We're going to talk a little bit about organic chemistry, hit some of the highlights, and that will be it for lecturing, I think, after we're done. We are, by the way, I'm just going to go kind of off the top of my head and hit some of the highlights of it and everything. And then we'll kind of go, yeah. There is no notes. I'm just going to kind of, like I said, just kind of go off the top of my head and do it. You really won't be responsible for too much of anything from this chapter, I think, but we do need to cover it. So in case you're going to organic, at least you'll see something, I suppose. All right. So let's start with it here. So organic chemistry, as most organic books start with, is really the study of carbon compounds. And one of the important things about carbon, as you hopefully remember, is carbon's got basically 4 valence electrons. So one of the most important things as you kind of do organic and super common errors that people make is uh, carbon is a group period 2 element, which means it does has to obey the octet rule, which means carbon should always pretty much have 4 bonds. Um, for some reason, when people start to do organic, they just want to keep throwing bonds onto carbon, and ends up with like 92 bonds on it and stuff like that. But essentially, should only have 4 bonds always. Also, a reminder, because a lot of organic compounds contain carbon and also hydrogen, a reminder that hydrogen, right, obeys the duet rule, which means it should only have 2 electrons. So again, super common errors that people make when they sort of start organic is just to put like way too many bonds on carbon. For the most part, a lot of organic compounds, carbon doesn't have any lone pairs on it, so it will really continue to make bonds with it. The basics of sort of organic molecules, or the basic backbone of organic molecules, are really carbons attached to carbons. So you got a bunch of carbons really attached to carbons, and attached to those carbons are hydrogens. And that is really the sort of makeup of pretty much all organic molecules. And what that does is it does give organic molecules some certain types of properties. So a couple of things that you also should probably remember. Obviously, the carbon-carbon bond is a nonpolar bond. It has a difference in electronegativity of 0 if you use like the Pauling scale and kind of subtract the 2. Also, the bond between carbon and hydrogen has a difference in electronegativity if you use the Pauling scale of about 0.4, and that 0.4 on the Pauling scale is basically the limit for also nonpolar bonds. So essentially the basis of all organic molecules are nonpolar. And a couple of things that are different for organic molecules than, say, versus ionic compounds is because they're basically nonpolar, they will use things like dispersion forces for a lot of their interactions. And if you remember, dispersion forces are the really weak intermolecular forces, like an instantaneous dipole, a induced dipole type situation. They typically will also have very low melting points and boiling points. And that is because they are held together by these really weak dispersion forces. So remember, melting points, freezing points, boiling points, they're affected by really intermolecular forces. So how strong a molecule could hold itself together with another similar molecule. And obviously, since these are the weakest, they typically have very low melting points and boiling points. That's why a lot of the early sort of organic compounds like methane, ethane, propane, butane, a lot of those guys are gases. And again, they're held together by these really weak sort of forces. In general, they're also a lot of times going to be insoluble in water. And that is because, again, water obviously is polar. So remember that in terms for things to be sort of soluble in each other, that's the idea of like dissolves like, right? So things that use similar intermolecular forces, will be soluble in each other. So oftentimes when you take an organic compound, which is trying to use dispersion forces, and you take something like water, which is using hydrogen bonding, there is no long way for those two to interact and kind of maintain that interaction. And they typically will separate out. And for example, if you've ever seen an oil spill in the ocean, right? Oil is pretty much an organic compound. It just floats on the top. And typically the organic layer, for example, if you mix it with water, typically your organic layer is up on top and your aqueous or water layer is on the bottom. So they do separate out from each other. Now, as you go through different types of organic compounds, what happens is as we go through it, some of these hydrogens may be replaced by other elements like nitrogens, oxygens, halogens. And by replacing some of these hydrogens with other sort of elements, they do give you different sort of organic groups and functional groups. And it also does change, for example, some of their properties. So for example, if you took out a hydrogen and maybe replaced it with a OH group, now you have, because of this OH group, what is known as an alcohol. And even though a lot of organic molecules will sort of have this situation that develops where part of the molecule is really nonpolar, but they will have this sort of group over here that actually is a polar group. And that OH group is, again, a polar group. Now, by having this OH group here in this alcohol, what that allows is alcohol, which is methanol, by the way, it is actually able to very easily now interact with something like water through hydrogen bonding. Hydrogen bonding is a bond between hydrogen and an electronegative atom like nitrogen, oxygen, or fluorine. So these guys actually are really soluble in each other. So that's what happens as you go kind of deeper into organic chemistry. You get these different sort of organic molecules where we've substituted out some of these hydrogens for other elements, and they can, like we see here, kind of change some of the properties of it. This actually has a pretty high boiling point in comparison to just a basic organic compound that's just carbons and hydrogens. Any questions on that there? Now, carbon itself and the basis, like I said, of a lot of organic compounds are carbons attached to carbons. And carbon can form single bonds with other carbons. So you can have carbon-carbon single bonds. These are the type of compounds which are known as alkanes. And alkanes, this is sort of like what is referred to as the functional group, which is the carbon-carbon single bond. The functional group within a sort of organic compound is really the part of the compound or the molecule that makes it a specific type of organic molecule. So if you have just all carbon-carbon single bonds, these are what are known as alkanes. They also can make double bonds with other carbons, like so. And obviously I'll go this way, put in just some lines there. And we'll have a couple lines here. These, by the way, is another type of organic group where the carbon-carbon double bond is the functional group. This is what is referred to as an alkene, ENE. And for example, carbons also like to make triple bonds with other carbons. And this is a type of organic compound which is known as an alkyne, I'm sorry. This is an alkyne, YNE. So just by, for example, adding bonds, we do change the compound and we change some of the characteristics. For example, one of the things that happens in organic chemistry when you actually do make a bond between, for example, two carbons is, again, it does need to maintain sort of that octet rule. So every time you make a extra bond between two carbons, you do have to sacrifice hydrogens. So if these were all hydrogens here, when we make this double bond, in order to make sure carbon does not go over 8, we do actually lose 2 hydrogens. When we make the triple bond, we lose 2 more hydrogens along the way. In general, alkanes have a general formula of CnH2n plus 2. N is the number of carbons. And so, for example, here we have 2 carbons. 2 times 2 is 4, plus 2 is 6 hydrogens it should have. And that's the general formula for alkanes, which are single bonded. Because we do lose 2 hydrogens along the way here, CnH2n is the general formula for alkenes. Here again, if we take a look, we have 2 carbons, which means N is equal to 2. 2 times 2 is 4, which would give us our 4 hydrogens. And again, when we put that last bond on here for alkynes, CnH2n minus 2. And again, we have 2 for N. 2 times 2 is 4, minus 2 is 2, gives us our 2 hydrogens. So every time you kind of put a extra bond on between 2 carbons, you typically do have to kind of sacrifice 2 hydrogens. The hydrogens are sacrificed, by the way, 1 on each carbon, so they're never usually the same carbons. So each carbon will lose a hydrogen when you do that. Any questions on that there? Now, in terms of when we look at sort of the geometry that occurs as well, when these guys sort of make these double bonds, single bonds, or triple bonds, we do see some geometry that occurs. So if we look at, for example, our guy will just go here. When we have this alkane, this has carbon in the middle, 4 electron pairs, and 4 bonds. And if you remember from geometry, that is the tetrahedral arrangement. And that has a bond angle of 109.5 degrees. So when it's all single bonded, all of those carbons will basically end up in a tetrahedral arrangement. And this is 109.5. When you pop on that double bond, we do change the geometry as well. Now, when we look, say, at this carbon, it actually has 3 electron pairs. Remember that when you're doing geometry, if you have a double bond or a triple bond, it counts as 1 electron pair and 1 bond as well. And it also has 3 bonds. So by adding that bond in, we actually end up with a trigonal planar geometry. And as you might remember, that's more of 120 degrees that occurs. And lastly, here, if we look at our triple bond and look at this carbon, once again, triple bond counts as 1 electron pair and 1 electron pair on the back end there. That is 2 electron pairs and 2 bonds. And as you remember, that is also a linear geometry with 180 degrees in terms of the bond angle. So as we also lose the hydrogens as we add bonds, we also change the geometry of the molecule as well. And one of the things that you do a lot with is also hybridization. So when we look at the hybridization of the carbons that are associated here, a reminder that if we look at this carbon here, it basically has 4 electron pairs. So that is going to be sp3 hybridize that carbon. If you don't remember how to do hybridization, again, a really quick way you could do it is there's only 1 S, 3 Ps, and 1, 2, 3, 4, 5 Ds. Not that you usually get to Ds in organic, but you just count up your electron pairs. So 4 electron pairs, 1, 2, 3, 4. That's an S and 3 Ps, so that is sp3. If we come over here, that is 1, 2, 3 electron pairs, 1, 2, and 3. So that is an S and 2 Ps, so that's sp2. And lastly here, if we look at this guy, we got 2 electron pairs, 1 and 2. So the hybridization of this guy is sp. Did you have a question? Question? Where's the 3 electron pairs on the second one? Yeah, so if you look at the carbon on the left, it is 1 electron pair, 2 electron pairs, and the double bond counts as 1. Yes, typically if you do hybridization or you do geometry when you have multiple central atoms, you do them from individually. You kind of put your hand over that side and kind of block it out and just look at it. The bond in the middle counts still for each of them. Yeah. Other questions? Yeah. What's that? Yeah, they're both actually sp hybridization, both of the carbons, but you would do the same thing. You kind of put your hand and not look at this side, but you would look at this, which would be one electron pair and two electron pairs. Yeah. Other questions? So the hybridization is kind of important. And again, sp2, and sp3 hybridization. By the way, a reminder that as you may remember, hopefully, right? If you have a kind of single bond, right? That is typically a sigma bond, right? And that is a result of head-to-head overlap of the orbitals that are coming on. When you have a double bond, that is a result of a sigma bond and a pi bond. And the sigma bond is the orbitals coming head on. The pi bond, for example, occurs from unhybridized p orbitals through sideways overlap that makes it. And obviously with a triple bond here, you have a sigma bond and two pi bonds. And in this case here, because it's only sp hybridized, you have two unhybridized p orbitals, these guys, and each one will do side-by-side overlapping and make the double bond and the triple bond of those unhybridized p orbitals. Any questions on that there? So when we talk about organic compounds, we also talk about some different types of formulas, the way that we write it. So for example, if we have C3H8, that obviously is the molecular formula. We could also kind of draw it out pretty much like a Lewis structure, where we just draw out everything. It'll look something like this. This is what is sometimes referred to as the expanded structural formula. We also can do what is referred to as the condensed formula, and really the only difference kind of between the condensed formula and the expanded structural formula is we really just don't draw out the hydrogens. So here, instead of drawing out the hydrogens, we just kind of condense them down, and this is what is referred to as the condensed formula, or some people call it the condensed structural formula. We also have, most common, if you take a real organic class, unlike fake organic classes, but if you take a real organic class, most of the time people draw them in what is referred to as line structure. And line structure is just a basic structure. It's kind of a minimalist structure, if you will. And basically everywhere the line ends, everywhere kind of two lines come together are carbons. So this would be a carbon, that would be a carbon. You clearly don't usually put the circles. That would be a carbon as well. And each of those carbons would have the appropriate number of hydrogens attached to it. That would be hydrogen, hydrogen, and hydrogen, 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 and hydrogen. So a line structure really is just a basic structure. Again, everything is carbon. If there's something that is not carbon, they will actually draw it. So, you know, if you had something like this and it was a bromine, they would actually put the bromine on there. By the way, also confusing to people sometimes is they just see a line with nothing drawn there. And again, a line with nothing drawn at the end is also a carbon at the end with the appropriate number of hydrogens. So very commonly, if you take a true organic class, line structure is typically how you draw everything. It kind of keeps things a little bit neater. There's not a lot of hydrogen drawn in there and stuff like that, so things don't get so crowded. Any questions on that there? Now, we were talking a little bit about functional groups, so let's just talk about the different sort of functional groups there are in organic chemistry, and there's a lot of them. And they do, again, have different properties depending on sort of what the functional group is. We talked about a second ago, the carbon-carbon single bond is essentially alkanes. Those are really your simplest sort of organic molecules. Carbon-carbon double bond or alkenes. Carbon-carbon triple bond are alkynes. We have OH group, as we saw earlier, that's an alcohol. We have what is known as a carbon-oxygen double bond to a hydrogen. That is an aldehyde. If you see a kind of 3-carbon run with a carbon-oxygen double bond in the middle, that is a ketone. You got an ester, which is a carbon-oxygen-carbon sort of run. You have a carboxylic acid, which is a carbon-oxygen double bond and an OH. And sometimes you'll see these written with an R on them, and the R is what is referred to as an alkyl group. But really what it is, it's just a carbon-containing group. So if you see kind of like an R written next to some of these functional groups, that really just means there's a bunch of carbons sort of attached or some type of carbon group attached to it. There's also esters, which is a carbon-oxygen double bond to an oxygen to a carbon. That is an ester. Esters are responsible for a lot of like smells that we smell, things like bananas and those type of things. We have some nitrogen containing guys, which are amines. Amines have a group that is similar to ammonia. They're kind of like ammonia derivatives. So it has a nitrogen containing group. There's also amides, which kind of looks like a carboxylic acid with an amine group on it. So that is an amide. There are also aromatic. Aromatic compounds contain an important compound in organic chemistry. This is known as a benzene ring. And these are sometimes referred to as aromatic. It is basically 6 carbons, 6 hydrogens, and 3 double bonds within that structure there. So if you kind of go through here, maybe draw it a little bit better than I did over there. Looks like this. So again, at each of these spots are carbons, and each carbon will have 1 hydrogen. And again, it has 3 double bonds, and that's benzene. So something that has that as sort of the base of it will be a aromatic. There's also sulfur containing groups, which has SH. Yeah. Yeah. R is really it's like an alkyl sort of group. It's basically just a carbon group. Yeah. So for example, if you had something like this would be your R group. It's a carbon containing group, basically. Any of these guys, yeah, for the most part. Sometimes, a lot of times, then you'll see R's written next to these guys. And basically, it just means it's attached to some type of carbon chain, basically. Could be 1 carbon, 2 carbons, 3 carbons. Could be just be some type of carbon chain. An alkyl group. This part right here, a carboxylic acid. That's like acetic acid, like vinegar. It's basically a carboxylic acid. This is a thiol, this sulfur-containing group. And lastly, we also sometimes will substitute out some of those hydrogens for halogens or group 7. And that is basically a carbon attached to an X. X could be a halogen like Cl, Br, etc. This is what is sometimes referred to as an alkyl halide. It's basically where you kind of just substitute out one of those hydrogens for a halogen. Again, as I mentioned a second ago, these different groups do have different properties, and some of these groups, as I saw with the alcohol, can give it, pretty good boiling points, can give it interactions with water. So as we talked about a second ago, the OH group allows something to hydrogen bond with water. Also, the presence of this carbon-oxygen double bond in a lot of these functional groups. This is what is known as a carbonyl carbon. And this carbonyl carbon is actually a polar sort of group, oxygen being more negative, carbon being more positive. Yeah. I'm sorry. I think this is actually not an ester. This is an ether. Thank you. Yeah. Yeah. So the carbon, oxygen, carbon here is actually an ether. And the other one there is an ester. Yep. Thank you. This carbonyl carbon is a polar group. It is also where a lot of sort of rearrangement happens when organic molecules sort of attack. They're sometimes referred to as nucleophiles and electrophiles. And again, they come in and kind of break bonds, opposite attraction here. Again, the presence of something like an OH group also is a polar group. The one that we see in a carboxylic acid actually has both of those groups. It has this sort of carbonyl group, also has this alcohol group, which gives it many places to sort of interact. So something like water, our alcohol here has a pretty high boiling point. A carboxylic acid is one of the things that can actually sort of beat it because it has both of those groups as well. But things like solubility and other properties do start to diminish as the nonpolar part of the compound gets larger. So if you had something like methanol, like we had previously, and then you decide you just want to stick on there a bunch of carbons with all hydrogens. So what happens in terms of like something like solubility is this guy here is going to be pretty soluble because it's relatively small. And the idea here is if something wants to be sort of soluble within like water, what you have to do is replace water interactions with similar sort of interactions. What happens though on this guy is we now have a pretty big non-polar part to the molecule and a really kind of small polar part. And what ends up happening because of that, the big non-polar part essentially gets in the way of the interaction that it can do with water. It's sometimes referred to as steric hindrance. It's like a big thing in the way. So it makes it really hard for water to get in there. Also, this thing's really big, so it's not going to fit really well with the water molecules as well. So this thing would have pretty much no solubility in water, even though it still has the OH group, because it has that really long sort of non-polar part. I would say in general, as you go through the different functional groups within organic chemistry, kind of like five-ish or more carbons, you really start to see if it's something that can interact well with water. It has a functional group that can interact well with water. Once you get to five or more carbons in a lot of those guys, you do start to see the solubility drop a lot. Also, though, if you had, say, multiple OH groups, the opposite effect would happen. You would actually see the solubility start to increase because everywhere there's those OH groups, it has a way to interact well with water. Was that? That molecule, so it's kind of interesting. A lot of organic compounds, they kind of have polar parts, if you will. And overall, it technically would be polar because it does have a polar part, but it has a lot of non-polar parts. So overall, something like that on the bottom essentially would be kind of in the non-polar region because of how big that non-polar part is. Yeah, it does. So for example, this pretty much will behave like a nonpolar molecule. It won't be very soluble in water or anything like that, even though it's got that little part on the on the right hand side because it's just too big. It gets in the way. As opposed to this, which is much smaller, it's able to actually interact and be polar. Correct. It's like with the difference in electronegativity. So oxygen in this case is more electronegative than hydrogen. So you have the, just like you have in water, basically, that is going to be more negative on this side and more positive on this side. And again, just like you have with water, that's what's going to allow it to hydrogen bond as the hydrogens in water is more positive and the oxygens are more negative, and that's where it's able to kind of do that interaction. Here again, just this part of it just gets in the way and it really prohibits it for doing it. So like I said, in most of those guys, if you kind of look at this sort of chart here, anywhere there's like an OH group or maybe even a carbonyl group or something like that, what ends up happening is you see a really big kind of decrease in solubility once the kind of nonpolar part of the molecule reaches like 4 or 5 or more carbons. It really does decrease the solubility a lot. Other questions? Yeah. So let's talk a little bit then about let's talk a little bit about alkanes here. So as I mentioned before, alkanes are really these kind of simplest organic molecules you could have. They basically are all single bonded. They are also sometimes referred to as hydrocarbons or hydrocarbons. Hydrocarbons are pretty much like the name sounds like. They are compounds that basically contain only carbons and hydrogens. So this would be obviously a hydrocarbon. This would also, by the way, be what is referred to as a saturated hydrocarbon. And a saturated hydrocarbon is basically a compound that has all single bonds. And essentially, what it has is the maximum number of hydrogens you could have per carbon. So in this case, the maximum number it could have for each of those carbons are 3, and this would be a saturated hydrocarbon. An unsaturated hydrocarbon is where you have at least one double bond, or maybe even more. So for example, when we make that double bond, as we talked about a second ago, because we have to make that bond and keep the octet rule intact, we do lose some hydrogens. So now we don't have on each of those carbons the maximum number of hydrogens possible. And this would be what is referred to as a unsaturated hydrocarbon. So when you go to double bonds or even triple bonds, you get what are referred to as unsaturated hydrocarbons. Now, alkanes have the general form of CnH2n plus 2, and they really are the simplest sort of organic compounds. They're also sometimes really the important organic compounds because a lot of names that you have for other types of organic molecules, they oftentimes will fall back to the alkane name. So the alkane, you can almost think of it as like the basis of like all the other sort of names that you have. So for example, if we run through the first 10 alkanes, which are kind of important, if we have our CnH2n plus 2, if I have one carbon, that will essentially give me, oops, come back. That'll give me 4 hydrogens. That is what is known as methane. That is pretty much your simplest organic molecule you can have. If I have 2 carbons, 2 times 2 is 4 plus 2 is 6. I will have 6 hydrogens. That is what is known as ethane. If I have 3 carbons, 3 times 2 is 6 plus 2 is 8. That is propane. I have 4 carbons. 4 times 2 is 8 plus 2 is 10. That is butane. If I have 5 carbons, that will give me 12 hydrogens. That is pentane. And again, the connection here is carbons attached to carbons and the hydrogens attached to all the carbons. C6H14 is hexane. C7H16 is heptane. C8H18 is octane, like in your car when you fill it up. C9H20 is nonane. And lastly, first 10 here, C10H22 is decane. You can see these are all alkanes, ANE, and you can see that they all end in ANE. So these are your simplest ones. Once again, they're all connected carbon to carbon. So for example, if we want to draw butane, 1, 2, 3, 4 line structure there. You want to do pentane, 1, 2, 3, 4, 5. Hexane, 1, 2, 3, 4, 5, and 6. Heptane, 1, 2, 3, 4, 5, 6, 7. Octane, 1, 2, 3, 4, 5, 6, 7, 8. By the way, again, all these are single bonded, and it is because of that tetrahedral geometry and that 109.5 degrees that we give typically when we draw them. This zigzag shape is sometimes referred to when you do line structure. And again, that's because of the single bonds and the geometry that's happening there. By the way, a lot of the naming, and as I mentioned before, all come back to sort of these names here. You just do some slight changes to it that will change the meaning. So for example, just to give you an idea here, if you look at something like, we'll do our 1, 2, 3, 4, 1, 2, 3, 4, 5. So that is C5H12. That's all single bonded. Again, 1, 2, 3, 4, and 5. That's pentane, ANE. Now, if I take that same deal, 1, 2, 3, 1, 2, 3, 4, 5, and maybe I put a double bond right about there, that's going to be C5H10 in this case. And instead of pentane, this will be 1, 2, 3, 4, 5. This will be pentene, ENE, because this is now an alkene because it has a double bond as opposed to our alkane. By the way, you do has to give the location of that double bond, which would be at carbon number 2. This would be 2-pentene. By the way, this is 1 carbon, 2 carbons is where the double bond starts. So that is where the 2 comes from, the actual location of it. Now, when you come here and you decide to do this, we'll go. We now have a triple bond here, and that would be C5H8. And this would now be 2-pentine, YNE, yes? And that's because this is an alkyne. Now you may be wondering where the carbons are. We got 1, 2, 3, 4, and 5 carbons, yeah, right there. Sometimes when people draw line structures for triple bonds, people miss the carbons actually on both sides of the triple bond. They just kind of roll it into the other lines and stuff like that. What you see here again is geometry changes. So a lot of times you'll see that triple bond drawn maybe more straight because of the linear geometry. But again, you can see that all 3 of these names are really based off of the alkane name. By the way, it also goes with other functional groups as well. If you had something like this, I want to do line structure, but I'll just do it this way. 1, 2, 3, 4, 5. Do that. If we look at this, this has 1, 2, 3, 4, 5 carbons. 5 carbons would mean that it is based off of pentane. It has this OH group, which is the functional group for an alcohol. So this would then be called pentanol, OL, because it's an alcohol, OL, right? So that's sort of how some of these guys go. When we name things in organic chemistry, which we'll get a little bit into today, but when we name things in organic chemistry, it's all about giving people the location of where you could find everything within the carbon chain. And if we look at this, this is carbon number one. And it's carbon number one because in this case, what we want to always do is wherever sort of the functional group is, should always get the smallest number when you're numbering the carbons. So we could have started over here with one, but that would give that carbon at the end 5, which obviously is a larger number than 1. So we would start right to left in this case. And this would actually be 1 pentanol. Once again, the 1 would indicate where on the carbon chain that OH group is located. Do you have a question? It has to really do with the geometry of it. So when you put the triple bond in, it goes straight. So sometimes you'll often see the triple bond kind of draws in line structure where it straightens out. You can, it depends on your teacher. Sometimes they won't really care and they'll go, you could kind of just triple bond it up like that. Or sometimes teachers will want you to kind of show it with the geometry and stuff like that. So it kind of depends on your teacher. If you're taking a real organic class, they might want you to kind of straighten it out. But that's what happens. Just like here, technically, maybe not perfectly drawn. This is more of a trigonal planar type geometry that occurs there. Other questions? So again, like I said, we do sort of fall back to the alkanes a lot for how we name things. When we look at carbons as well, another really important sort of thing in terms of carbons is we could classify carbons, and we could classify carbons as either primary, secondary, or tertiary carbons. And when we look at carbons, sometimes it's important to know, is it a primary, secondary, or tertiary carbon when you look at it? So if you look at something like this, for example, do this. And if we were to look at this carbon right here, this would be what is referred to as a primary carbon. And that's a primary carbon because this is personally the way I do it, but some people will do it differently. But you want to look at, probably the easiest way to do it is to look at how many carbons are directly attached to that carbon. So directly attached to that carbon is one other carbon. So it's a primary carbon. Another way that they sometimes teach people in organic is you count how many hydrogens it has. In this case, it has 3 hydrogens, so it's primary. But to me, it just seems logical to go count the carbons. Attached to 1 carbon is primary. Attached to 2 carbons is secondary. Attached to 3 is tertiary. But some people will teach you to count the hydrogens. 3 hydrogens primary. 2 is secondary, and 1 is tertiary. So if we look at something like this, let's do this. Don't draw it out too much room there. We'll do that and do this. So if we look at the carbon here in the center, this carbon is directly attached to 1 carbon, 2 carbons, and that would be a secondary. By the way, when you do see it written like I did there on the left, CH3, the connection is actually still carbon to carbon. Sometimes people will write it like that. Sometimes people will write it a little bit better, and they'll write it as for this guy, like H3C to indicate that it's attaching that way. But if you do see it written like this, it is a carbon to carbon attachment that's happening there. Tertiary carbon is one where the carbon you're looking at is essentially attached directly to 3 carbons. So we look something like this. So if we look at this here, a tertiary carbon would be this guy. It's attached to 1 carbon, 2 carbons, and 3 carbons. And that would be a tertiary carbon, the guy in the middle. So for me, I personally like to count how many carbons is directly attached because it gives you the actual number it is. If you see 3, it's tertiary. If you see 2, it's secondary. If you see 1, it's 1. But again, like I said, very commonly, they'll tell you to count the hydrogens. And it's kind of backwards. So 3 hydrogens primary, 2 secondary, and 1 tertiary. Sort of any questions on that there? So let's talk, yeah. No, so what we're talking about here is if you're counting hydrogens, is how many hydrogens are directly attached to the carbon. So in this case, it would be 2. In this case here, it would be 3. And in this case here, it would only be 1. Yeah. So again, that's a very common way. Sometimes people are taught to do primary, secondary, tertiary. I personally like just carbon to carbon. It tells you basically, what it's going to be. Other questions? Okay. So let's talk about a couple things here. Let's talk about actually naming, and let's talk about how we name some alkanes. And typically speaking, when you go to name things in organic chemistry, you usually want to go with the IUPAC way. That's the International Union of Pure and Applied Chemistry. Earlier, people were asking who comes up with these rules. That would be those guys. They come up with all the rules of how you name all this stuff and the weird stuff that you do when you do it. That is usually the name that you want to go for. One of the things that you'll learn really quickly, though, in organic chemistry is there's a lot of names for the same thing. There's like the IUPAC name, there's like a systematic name, there's a common name, there's a name Joe's been calling it for 40 years, so you could have like the same thing that has 3 different names. An example of that would be, very common example would be this guy here. This guy here is technically 2-propanol. It's also isopropyl alcohol, and it's also known as rubbing alcohol. So these are all the same names for the same thing. And that happens a lot in organic chemistry. There's a lot of sort of historical names, a lot of common names that are used. But usually if you're kind of asked to name something, a lot of times you do want to kind of go with that really kind of formal name, which is the IUPAC way of naming. And that's the important thing. Now, when we go for the IUPAC way of naming, there's a couple of really important things when you look at a compound and you want to name it, for example, an alkane. There are, for example, what is sometimes referred to as a straight chain. And a straight chain here is pretty much what it sounds like. It just goes straight across. There's also chains where as you go straight across, there are some what are sometimes referred to as branches, like on a tree. There's branches kind of coming off the main part of it. I won't draw all the hydrogens here, but this is what is sometimes referred to as a branch chain. And there's also cyclic sort of structures. And cyclic structures are like a straight chain where the 2 ends decide just to kind of come together and make like a ring type structure. And those are very common as well. So for example, a lot of times those cyclic structures are sort of drawn and it's kind of geometrical shapes like triangles, squares, and those type of things. But basically what happens here is the 2 ends come together. And by the way, when you have that in an alkane situation, you also do lose 2 hydrogens because the 2 ends come together. It's got to lose those 2 hydrogens to make the bond. So what happens though is when we go to sort of count these guys, there is going to be a main chain, and a main chain will have the longest carbon chain that's present. And there will also be some groups that are attached. And so there'll be some groups attached. And if they are carbon groups, they are going to be referred to as alkyl groups. And alkyl groups are basically carbon groups. They are related to those alkanes, for example. So for example, if I had this, and maybe I had this, right? I'll do this. So when we would look at this, for example, one of the first things you always want to do is find the longest continuous carbon chain. Now, the longest continuous carbon chain means that you basically start in one direction and you keep counting until you hit a dead end. You can't go backwards, so you can't like back up and go around. You go in one direction until you hit a dead end. So for example, if we were going to count this, We could start left to right and go 1, 2, 3, 4 carbons, and obviously we hit a dead end. We also could, by the way, and you should always, by the way, check all your options because the straightest one is not always going to be the longest. We could go this way, 1, 2, 3, and then go up. That's also 4, which would work. We could, if we wanted to, go this way, 1, 2, and up, which is only 3, which obviously is the shortest. So in this case, there's actually 4 carbons. It's the longest chain. You could actually get to the 4 carbons 2 different ways. It doesn't really matter which way you want to choose. My recommendation is if you have sort of a straight shot of carbons that's longest, go with the straightest one. That's usually easier to see. So I'm going to go with the blue there, which is our 4 carbons, which is the longest. Now, when we look at this, we have this group over here, which is technically not part, this is not part of the longest carbon chain. So this guy here would be what is referred to as a group. And more specifically, this would be an alkyl group because it's a carbon-based group. Now, this guy looks very similar to one of those alkanes that we saw. And it looks very similar to CH4, right? CH4 has 1 carbon. This group has 1 carbon. CH4 looks like this if you draw it. The problem with if we wanted to put CH4 onto this ring, just like it is, we wanted to attach this to that carbon there, we now would have 5 bonds, right, to that CH4, and that is too many bonds, too many electrons, going to go over the octet rule. So what an alkyl group is it's based off of those alkanes, except that it is going to be missing a hydrogen. And because it's missing a hydrogen, that gives it a place to attach to the long chain and still maintain the kind of 8 electrons or 4 bonds. So when we look at the CH3 here, it will look something like this. And where it has now is a spot on it that it's able to actually attach into the main chain. Now, not surprisingly enough, as I mentioned a second ago, CH4 is what it's based off of, and that is methane. But this is an alkyl group, which means we drop the A and E. And this CH3 is what is known as a methyl group. If you had a 2-carbon group that had 1 less hydrogen than ethane, it would be an ethyl group. If you had a 3-carbon group that had 1 hydrogen less, it would be a propyl group. So if you take off a hydrogen off of any of those alkanes that we saw on the previous page, that would turn it into a group where it has an attachment point, and you basically would drop the last part of the name and put YL, propyl group, butyl group, pentyl group, and that is how we kind of name alkyl groups. How we name like halogens is kind of how we named halogens when we did our naming a second ago in the last chapter. You had fluoral, chloral, bromol. So those are named very much like what we just did in the previous chapter. Now, we talked about a second ago, kind of primary, secondary, and tertiary. It does affect groups as well. There are certain groups based on where the attachment happens. We'll give it a special name. So for example, if we take propane, which is this guy. This is just propane, which obviously is our 3 carbons and our 8 hydrogens. If I take off one of these hydrogens, or any of those hydrogens at either end, these are all primary carbons. Both of those guys are primary carbons. And if I take any of those guys off, I'll do the guy on the right there. What I'm going to actually get is a connection right here at the end. And this would be what is known as a propyl group, kind of or a normal propyl group. But I actually have an option in this case to go to this carbon, which is actually a secondary carbon, and I could take a hydrogen off of there. And that would give me this guy here, basically CH3, CH, the connection is going to be right there, CH3. Because I took it off and the connection is actually going to happen at the secondary carbon, this is what is known as isopropyl group. So there are certain groups that have special names. based on where the hydrogen comes off and the connectivity happens. If it happens on a secondary carbon or even a tertiary carbon, there's something known as T-butyl, which T stands for the connection is happening on the tertiary carbon on that butyl group, and that's where it's attaching in. So there are some historical sort of groups that have special names that you sometimes come across. Isopropyl is a very common one, T-butyl, sec-butyl. Sec-butyl means it comes off the secondary carbon. So those are common sort of names. All right, so we have groups, we have a main chain. So when we go to name something, these are sort of the steps we want to follow for alkanes. Like I said before, we're always going to look for the longest carbon chain. And that's going to be the base of your name, basically. And that probably should match an alkane name. So you count up and it should match maybe it's propane, butane, something like that. Then you want to identify, you want to ID all your groups that are attached. Once you've identified the groups that are attached, once you have your longest carbon chain, the next thing you want to do is number your longest carbon chain. Now, when we go to number your longest carbon chain for alkanes, specifically, we want to give the smallest number to any groups that are attached. So the groups that are attached to that main chain get the smallest number. So that means you could go left to right in numbering, right to left in numbering. And it is as simple as if you go left to right and you got like a 2 and a 3 versus right to left where you got like a 4 and a 5. 2 is less than 4. That is the way you want to go. So it's just the smallest number for the groups. Once we do that, we want to go all groups in alphabetical order, regardless of prefix. And we do use prefixes in these namings. So if you have, say, 2 of the same group in the same molecule, they don't have to be on the same carbon, but in the same molecule, say you have 2 methyl groups, you would call it dimethyl. If you had 3 methyl groups, you would call it trimethyl. So we do use sometimes prefixes like that. So when you're doing alphabetical order, you're actually going based on the actual name of the group rather than the prefix. Also, sometimes what confuses people is number is not important either. It doesn't have to go number-wise lowest to highest. It is based on alphabetical. So you potentially could have alphabetical. This guy comes first with a higher number than the next number. So the numbering is not important. Now, when we put it all together, there are a couple other rules. We do between a number and a letter, we do a dash. So a dash between any number and letter, or a letter to a number, also a dash. If you happen to have 2 numbers back to back, or even 3 numbers back to back, we do commas between those. So we do commas between numbers when we're naming it. So let's take a look at one here and kind of go through it and see. Maybe I drew one here. Let's see. What I got? I think it is. So let's say we did. Let me do this one. Let's say we have this here. We go this way. All right, let's see what I just did here. We got this, put some hydrogens in. Obviously here I'm drawing my condensed formula here. All right, so I think I did all right. All right, so we're looking for, first off, the longest continuous carbon chain. So again, you might as well just go straight across and count. We got 1, 2, 3, 4, 5. So that looks good. We also could go this way. 1, 2, come up, 3, 4, 5. So that would also give us 5. We also could go this way, 1, 2, 3, 4, 5. So it looks like we have multiple options, but 5 seems to be the biggest. Again, in this case, what I'm going to do is take the straightest one because maybe it's easier. I also recommend maybe sometimes putting a box around it or something, the longest carbon chain, so you could kind of recognize it. When I do that, I again have some things that are considered groups. So I have this guy here, that's considered a group. And I have this one here that's also considered a group in this case. So getting to our name here, longest carbon chain, those are all single bonded carbons. They're an alkane. There are 5 of them. So the base of our name is going to be pentane. So that is the base of the name, the longest carbon chain. Now what we want to do is kind of look at our groups and sort of identify the names of those guys. This is a 2-carbon group. Again, it's a group, which means it's missing a hydrogen, but the 2 carbons is important. 2 carbons for an alkane is ethane. And since this is a group, this would be a ethyl group. Put the YL at the end of it. This is a chloral group, like we did before. Any questions on that so far? Now that we have this, we want to number the longest carbon chain. And remember, you basically have 2 ways to do it. I'm going to go left to right here. So 1 carbon, 2 carbons, 3 carbons, 4 carbons, and 5 carbons. Going in this direction, I have a group at carbon 2 and a group at carbon 3. So those are where the 2 groups would be in that direction. If I go in the opposite direction, we'll do it in orange. 1, 2, 3, 4, and 5. So going in the orange direction, which would be my other option, I end up with a group at 3 and a group at 4. So in this particular case, which way gives me the smallest? It is the blue. So the blue direction here would actually be the correct direction, as it gives me the smallest set of numbers. And again, in organic, it's always about smallest. It's basically what you're looking for. Longest carbon chain, everybody else in terms of numbering, you want to get into the smallest sort of set of numbers. At this point, what that would mean is my chloral would actually be 2-chloral, again, numbered to letter, dash in between. This would be 3-ethyl. And now I'm ready to put it together here alphabetically. I'm going to look at E versus C. So C is going to come first. This then would be known as 2-chloral, 3-ethyl pentane. Any questions on that? Yeah. So the answer is no. You want to first prioritize just where any of the groups are, regardless of what they are. So you want to go whichever way will give those groups the smallest numbering. What can happen though is you could go kind of like left to right and right to left, and you can end up with like the same numbers, if you will, right? So you can end up like 2 and 3 going one way or 2 and 3 going the other way. At that point, what you would then want to prioritize is the alphabetical part of it. And if it makes a difference in terms of either going this way or that way, if you went right to left, that would give the alphabetical guy the smaller number, and then you would want to do that. Yeah. So it is definitely possible, and you'll come across, you get kind of like a tie in either direction. And then the next thing you want to do is kind of go to that. And that's sort of what you want to kind of follow with all organic naming, which is you end up with kind of a tie. Then you want to think about, okay, what's the next sort of important thing to look at? And that's what you want to do. All right, let's take a look at a couple more here. Maybe let's take a look at okay, so let's take a look, see how you're doing. Again, always want to look for your longest carbon chain. These are line structures. So this would be a carbon 1, 2, 3, 4, 5. Your other option really would be 1, 2, 3, come down as 4. You could also go 1, 2, 3, 4. And again, obviously those are smaller than 5. So 5 seems like the longest. Again, if you want to kind of box it up or whatever you want to do there. So 5 being the longest means the base of our name is going to be pentane. Now, when we look at this, we do have a couple of things hanging out there. We have here, which is a chloral group. We have just a lonely line hanging out here, and a reminder that if there's nothing written at the end of the line and line structure, that is going to be a carbon with the appropriate number of hydrogens, which in this case would be 3. And that's actually going to be a methyl group that's hanging out there. Now that we have our groups, we want a number. You could probably just look at it and see that if you go left to right in this case, 1, 2, 3, 4, and 5, that's going to give you a smaller set of numbers than if you go right to left, because your first number going right to left is going to be 3. So that means we would have 2 chloral here, and this would be 3 methyl, again alphabetical, 2 chloral, 3 methyl, and a little pentane action there at the end. Yeah. Any questions on that one there? What's that? There isn't. There's just one. The 2 means it's at carbon number 2 on the chain. Yeah. And that's what the 3 means here. This guy's attached to carbon number 3. Other questions? Looking at this one here, we got 1, 2, 3, 4, 5 as well. You could also go 1, 2, 3, 4. That seems short. 1, 2, 3, 4. That seems short. You go 1, 2, 3, 4, 5. You could also go 5 that way if you wanted to. I think 5 is going to be a winner here. I think that's going to be it. I guess you go 1, 2, 3, 4. Yep. So 5 is going to be a winner. So we'll go with 5 across here. And again, that's going to give us pentane as the end of it. We do have this guy and this guy as groups. These again are just lines, and that means that each of these are methyl groups. In this particular case, we actually have then 2 methyl groups within the compound. So this is where we would use a prefix, and this would be like a dimethyl situation, as we have 2 methyl groups in the same compound. We do need a number. Again, looking at it, you could probably see if you go this way here, that is going to get you the smaller number. If you go the other way, you're going to end up with a 3. We do need to give the number twice here. So for 1 for each methyl group. And by the way, even if they were on the same carbon, you would have to give the same number twice as well. So if they're both on the second carbon, you would have to go 2, 2. They're on different carbons in this case. So this would be 2, 3 dash dimethyl pentane. Yeah. If you start from the bottom, yeah, but then that would be part of the main chain. So if you're saying you don't have to start an end. You could do this if you're asking 1, 2, 3, 4, and 5. You can do that, but what that then does is move your methyl groups right there. Yeah, and that's still going to be 2 and 3. Yeah, because that would then be part of the main chain. Yeah. Which is perfect. That's what I was saying before. If there's multiple sort of longest carbon chains, you could choose either one. They both should come out the same name, but sometimes just choosing the straighter one is a little bit easier. All right, one last thing here before we wrap it up here for today is if you have a name and you want to kind of draw the picture, which I personally think is the easiest thing to do because it basically tells you what to draw. Let's just go over kind of how to do that with alkanes. Let's say we had 2 methyl, 3 ethyl, and heptane. So whenever you have the name and you want to draw it, you should always work backwards in the name. So I would always recommend working in this direction. And this is the base of the name, which is heptane. So that automatically tells me how many carbons I should put. Heptane is 7. And I would just start with the 7 carbons. 1, 2, 3, 4, 5, 6, 7. I'm going to do more like a condensed structure. You could obviously do a line structure by doing the same thing. 1, 2, 3, 4, 5, 6, 7. Now that I did that, I'm crossing it out. What I now know is I have 2 methyl and 3 ethyl. The good news here is you're drawing it, so you could start numbering whichever way you want. You can number on the left as number one, you can number on the right as number one. So I'm going to call this my carbon number one on each of these. And because that's carbon number one, I'm going to go to number three and do an ethyl group. Ethyl is a 2-carbon group. If you just want to do the 2 carbons, you could just do that. I'll come over here and do my 2 carbons. I'll come here. Number 2 is a methyl. So we'll come here and put a 1 carbon there, and we'll put a methyl group there. At this point, I'm out of name. What is left is everything else is going to be hydrogens. And the thing to remember is carbon needs 4 bonds. So you want to put in as much hydrogens as necessary to get you to 4 bonds. This guy here has 1 bond coming in, which means it needs 3 hydrogens. This guy has 2 bonds coming in, needs 2 to get the 4. 2 bonds needs 2. 2 bonds needs 2. This guy has 1, 2, 3 bonds, just needs 1. This guy has 3 bonds, just needs 1. This has 1 bond, needs 3. This has 1 bond, needs 3. This has 1 and 2 bonds, needs 2. 1 bond needs 3. So that's the best way to sort of draw it, is kind of start with the carbons. At the end, after you put everything else on there, whatever's left over should just be hydrogens. If you're doing more of a line structure, you don't have to worry about the hydrogens because they're just implied to be there, so you don't have to actually draw them out. But that's always the way you kind of want to draw something, is kind of work backwards. It doesn't in the case of alkanes, because they're all single bonded. So with alkanes, because they're single bonded, they have free rotation around the bond. So you could draw it up or down. When you get into alkenes and some double bonds and triple bonds, what happens when you put a double bond or triple bond, it locks the carbons into place. So there is not that free rotation. And that gives you some isomers, like we sort of talked about a little bit, we're known as cis or trans isomers, which will lock those groups either being like above the double bond or below the double bond or opposite sides of the double bond. So in this particular case with alkanes, you're pretty free. You could put it on top or bottom because technically it's kind of the same rotation. That's also why when you draw something like this, if you called this carbon 1 and did it going in that direction, it's basically the same molecule, just turned, and it'll come out the same. Other questions on that? All right, we'll wrap that up today.